Thanks everyone for coming to our, it's actually a joint seminar between ACOM and EOL. And I am happy to introduce Elizabeth Asher, well known as Lizzie, as you know her. I'm going to say a few words about Lizzie. Lizzie is currently working as a serious research scientist at NOAA. Prior to this position, she completed her PhD in oceanography at the University of British Columbia, Vancouver in 2015. She has been an ASP postdoc at NCAR and a postdoctoral researcher at the Department of Land, Air, and Water Resources at UC Davis. In general, I think she is interested in developing instruments and instrument networks to measure concentrations of aerosol and trace gases that might improve data-driven approaches to air quality forecasting and climate modeling. And her talk today will be about airborne VOC observations. Thanks, Lizzie, for coming.
All right. Thanks, everybody. Thanks, Ivan, for the introduction. I'm really... Sorry, what? Hold on. Got it. So thank you for coming. I'm really excited to discuss the Whole Air Sampling Pilotless Platform, or WASPP. And a quick thank you to many of my co-authors who were great mentors while I was here at NCAR, or otherwise great people to work with. So as Ivan mentioned, I did a PhD at UBC in oceanography, and I studied one volatile organic compound, or VOC in particular, dimethyl sulfide. I was interested in better understanding the sulfur cycle and improving emission estimates of DMS. And I sought to do that by essentially developing instruments to measure DMS and other related sulfur compounds in the surface ocean. Today's talk, though, is about WASPP, and I'm going to discuss the motivation for building and designing this instrument, some design constraints, as well as laboratory calibration measurements that we made, and some side-by-side comparisons that we did. I'll round the talk out with measurements from the Colorado Front Range and a few conclusions and potential uses for this instrument. So the atmospheric boundary layer is temporally and geographically variable. And as well as between transitions of day and night, during the daytime, it's got a mixed layer that's driven by turbulence, but I hope to show that even that has some variability within it. So I really like this quote from Yi et al., a relatively recent paper. A typical assumption is that longer-lived species, such as oxygenated volatile organic compounds, or OVOC, are well mixed within the ABL, and that chemical lifetimes are much longer than turbulent mixing times. So, although I intend to show in the next couple slides that the latter half of this sentence is certainly true, the first part of this assumption, that longer-lived species are uniformly distributed in the ABL, I don't think is necessarily true. So, as I mentioned a moment ago, turbulence controls vertical mixing in the atmospheric boundary layer during the daytime. And turbulent eddies vary in scale, but they're all rather small, and turbulent mixing timescales are typically less than an hour. And of course, that is much shorter than the chemical lifetimes of many volatile organic compounds, or VOCs, with respect, for instance, to the hydroxyl radical, or OH. This table is showing a number of compounds I measured during this study, including alkanes, alkenes, aromatics, terpenes, and oxygenates. And essentially, the chemical lifetime of these species is between tens and hundreds of hours. So it's much longer than turbulent mixing timescales. And yet, even in a well-mixed atmospheric boundary layer, we can observe strong vertical gradients in VOCs, or volatile organic compounds. So there was a study done in the early 2000s in Mexico City that used tethered balloons at various altitudes to measure essentially VOCs and other trace gas species in the atmosphere. And this figure in particular is looking at several VOCs, propane, benzene, toluene, and at different times of day. So we're looking at dawn in the top row, mid-morning, I think, in the middle row, and noon in the last row. Along the x-axis is the concentration or mixing ratio of these species, and on the y-axis is altitude for all of these compounds. And essentially what we see is that even at noon, when we expect a well-mixed atmospheric boundary layer, we see strong spatial gradients in these compounds and spatial variability in the vertical dimension. Now, another paper that came out of this study showed that not only are there spatial gradients or spatial variability in VOC with altitude during midday, but you also see the same spatial variability in production products like ozone, which is pretty interesting. And this can occur, even as late as, say, 2 p.m., when we see nearly constant potential temperature with altitude and constant water vapor mixing ratios. The authors, I guess I should note, the authors attributed this spatial variability in the vertical dimension in ozone to a number of things, including plumes for precursors, differences in diffusion, and maybe most importantly, because there's a lot of spatial variability there, differences in the efficiency of ozone production due to differences in solar radiation from clouds, etc. So making UAV measurements in the atmospheric boundary layer is certainly not new. I just showed a study that used tethered balloons that has done this close to 15 years ago. And essentially, we have a number of means of doing that. That includes balloons, towers, and manned aircraft as well. But unmanned aerial systems, or UAS, can also measure atmospheric composition, and they can substitute for many of these platforms. And in some cases, they might offer actually some really advantageous features. For instance, while manned aircraft is expensive and opportunities to fly below 500 feet are limited, typically, UAVs obviously are relatively unrestricted below 400 feet. And towers are relatively few and unfortunately being dismantled, such as the Boulder Altitude Observatory, or BAO tower, which was taken down in 2016. And so that offers limited opportunities to constantly interrogate the atmospheric boundary layer. And then finally, balloon studies, which have been really useful, are beginning to be hampered by our current helium shortage. So that platform is becoming more and more expensive. And although you can use hydrogen in the place of helium, that introduces more difficult logistics and makes it potentially more dangerous to make these measurements. So just to summarize this introductory section, essentially VOCs are not uniformly distributed in the ABL, or certainly not always uniformly distributed. We have a number of traditional tools to make these measurements, but those may not always suffice. And essentially, UAS or UAV measurements can substitute for these platforms. So this field, the field of making atmospheric measurements from UAS or unmanned aerial systems, is rapidly growing. And in 2017, actually, the Earth Observing Laboratory here at NCAR had a community workshop. And although today I will be discussing largely a sensor suite or a single instrument that flies on a drone, one of the takeaways from this workshop is how integrated the sensor suite or instruments need to be with the rest of the platform, and how those really need to tie together well. And I'll actually discuss kind of the integration of a sensor suite on a platform in particular. So I've tried to convince you already that UAVs are a good means of making VOC observations in the atmospheric boundary layer, but of course there are challenges associated with doing this. When I set out to design and build the WASPP instrument, I had several vague objectives, which are pretty much listed here. I wanted to make multiple measurements of VOC and OVOC. I wanted to also measure ambient temperature, relative humidity, and pressure. And I wanted some ancillary measurements of GPS, system flow, system pressure, and battery life. Now, the challenges I quickly ran into were that it's actually difficult to make ambient or representative measurements from a UAS platform or unmanned aerial system. And also, I wanted to have sufficient sample for duplicate measurements from each of my canisters. But when you are already working with relatively tight size and weight constraints, that can be a challenge. And finally, I'll discuss one last challenge of trying to minimize sampling times for this instrument. So as I mentioned a moment ago, sensor placement is key. There are a number of places that you can put a sensor on top of a UAS, beneath a UAS, next to a rotor, beyond, kind of out on a boom. And there are a number of concerns that go along with this depending on the sensor. One I'll talk a lot about is quadcopter rotor wash. Depending on your sensor, having sufficient airflow may be a concern. Thermal heating may be a concern, especially if you've got a sensor located on top of a UAS, or off-gassing, depending on the construction material of your platform. So this is a Solidworks design courtesy of Steve Gabbard that basically shows our instrument on our platform of choice, which is a DJI Matrice 600 Pro. You can see that our inlet and sonic anemometer extend well beyond the rotors. And so this is clearly our final design that we've chosen to go with. And I'll explain a bit more about that in a moment. And we've done our best basically to consider sensor placement and as well as maximize sample volume. So we wrestled a lot with sensor placement actually, and we considered first putting sensors and our inlet, I guess, above the UAV shown here in figure A. But the problem with that is that we would be basically raising the center of mass, and so we might have a higher overturning moment and increase the instability of our platform. We're worried about flipping the drone and watching it crash and burn. So the next thing we considered was putting our sensor payload far below the rotors and trying to escape rotor wash in that way. But that makes the logistics of landing and taking off more difficult, and maybe most importantly, CFD modeling of the airflow underneath the drone showed that that is actually the most turbulent region underneath the copter, essentially. And then we considered various options, basically a ballasted and not ballasted boom, which is basically the design we decided to go with in order to get our inlet and measurements in a sustained hover out of that rotor wash. Now, in addition to using previous studies as kind of a guide, we also developed an empirical test to look at our in-flight measurements of temperature, pressure, and relative humidity, and use that as a gauge to decide if we were out of the copter rotor wash. So temperature, relative humidity, and pressure is expected to follow the -5/3 power law due to cascading energy from larger to smaller eddies in the atmospheric boundary layer. And we basically, for each sensor position, for instance, on top of the UAV here, compared our measurements in flight to the -5/3 power law. And we can see that during ascending profiles, for instance, with this sensor placed on top of the UAS, we can make maybe reasonable measurements of temperature, relative humidity, and potentially pressure. But when we do a sustained hover, we're mixing up the air even further, and we see that we get large deviations, peaks in the frequency spectra, as well as less variance than expected over the frequencies that we're measuring. A similar story kind of emerges when we looked at multiple sensor positions. So again, we looked at ascending profiles, a sustained hover for each of these positions, as well as descending profiles, which I'm not showing just in the interest of time. And essentially, you can see that it was easiest for us to make measurements during ascending profiles, and positions A and C seem to do an adequate job, or a pretty good job of that. However, during a sustained hover, it was much more difficult, and we essentially had to go to this third option of making measurements on a boom extended at least a foot beyond the rotors in order to have minimal perturbation in the natural variance of these signals. So these measurements also kind of showcase what happens on our ascending and descending profiles. in a sensor position. So this temperature, relative humidity, and pressure sensor is from one of our flights. And this figure is showing pressure, temperature, and RH on the x-axes, as well as altitude on all the y-axes. And this sensor was located basically just on top of the drone. And during the ascents, you can see pressure decreases with altitude. You can see small vertical gradients in temperature and relative humidity. But on the descents, you see these very non-physical changes, especially where you've got descent punctuated by sustained hover. And that may be due to thermal heating or potentially influenced by rotor wash. But they all happen to be in the same direction, which is pretty interesting. So I also mentioned that another design constraint we were interested in overcoming was having sufficient sample in each of our canisters to make duplicate measurements. So one key difference between our instrument and other whole air sampling instruments on drones is that we have pressurized our canisters using a pump. And we do that because basically if we collect a sample at altitude, especially if we're able to do longer, bigger vertical profiles, by the time we measure that sample on the ground, it would be slightly under vacuum. And so it would make analysis slightly more difficult. And in our case, because we think we need 120 milliliters for duplicate samples, it would make getting duplicate samples out of our miniaturized canisters difficult or impossible. And the last design constraint I want to discuss is something that we actually ran into after we finished building the WASPP instrument. So as you've seen from some of our last drawings, our canisters are all cylindrical or flat-bottomed. And we were worried that they weren't filling as quickly as we first supposed they would. And so we devised a lab test basically involving 2 concentrations of carbon dioxide, a 2-position valve in line with one of our canisters or our WASPP instrument, and a CO2 analyzer. And in the case of having a union in place of a canister or something with a volume of essentially 0, we would expect an instantaneous change. What we found, though, is that essentially our predicted fill time was much less than our actual fill time. And our predicted fill time is essentially just equal to canister volume times flow. But we think that filling our canisters was less efficient, potentially due to the edges of the canister or some kind of channeling within the canister. And so this plot is showing CO2 on the y-axis, mixing time on the x-axis. And for this canister, our predicted flow follows that equation to the left, and our actual lifetime is essentially 1 over this coefficient, which is a simple exponential model that's trying to fit our data. And this is the case for a 100 milliliter canister. But the same was true of a 50 milliliter canister or a 100 milliliter canister, essentially within the WASPP instrument. So we think that in part, we'd like to redesign the shape of our canisters based on this test. That is something for hopefully the near future. So our instrument in total, including its boom and inlet, weighs 6 kilograms. It has a number of different sensors. It's got an ambient pressure sensor, an ambient temperature and relative humidity sensor. It has a small GPS antenna that's actually separate from the drone so that we're not beholden to any one platform, and we could switch instruments, or drones, I guess, for this instrument. We have a system pressure sensor, a flow meter, the pump I mentioned a minute ago, a filter to remove particulates from the airflow, a small computer board that's a Raspberry Pi, and custom electronics board. And of course, the canister array, maybe the most important part. The inlet and the anemometer, as you can see from this lower figure, are out on the boom. This is another Solidworks drawing from Steve Schertz, and it just allows you to see all of those components perhaps more clearly, as well as the battery, which is hard to see in the last picture. And again, we've done that so that we could use any drone without tailoring our power system to a particular platform.
How many canisters?
So we designed it so that it could carry as many as 15 canisters, but we've currently been carrying 8. Part of that is based on our fill time and flight restrictions. So we can only fly for so long, and it currently takes us a long time to sample for each canister. So following every flight, the canister array is removed using 4 quarter-turn screws and loaded onto this extraction system that we built. And the extraction system basically just maintains, when you're analyzing samples on the trace organic gas analyzer, it maintains a constant overflow of sample past that inlet at ambient pressure. And again, this is just a Solidworks drawing, so you can see all of those components from the extraction system more clearly. So I'll play a very short video. You can hear that the WASP instrument's a little noisy, but you can also see that it's pretty stable as a platform. So we were happy with how it actually flies, and we were initially worried about it. Exactly, yeah. And it, at present, collects 8 whole air canisters per flight. It makes, thanks to the TOGA instrument, which has a really wide analytical range, it makes measurements within the range of less than 10 parts per trillion to as many as maybe 50 parts per billion. We have done our best to make ambient representative measurements of the atmospheric boundary layer. We are also I guess, happy that we think we're able to get duplicate subsamples out of many of these small miniaturized canisters, thanks to pressurizing them. It does take us 1 minute and 30 seconds to basically flush and then fill our canisters. I guess that's a little bit potentially overkill, but that's how long we're taking at the moment. And it also measures temperature, relative humidity, pressure, horizontal wind velocity, and system pressure and flow at about once per second. It has a computer programmed sample collection system that is just based on altitude and otherwise geographic location. So to summarize this section, our total payload weight is 6 kilograms. We have a canister array that easily detaches for analysis. It samples VOCs, it measures temperature, pressure, relative humidity, 2D winds, like I just said, system flow and battery power. It minimizes the impact of rotor wash, as well as UAV thermal heating or off-gassing, and it maximizes canister sample volume. And we're also seeking to minimize the sampling time. Following its construction, we did some laboratory tests basically in the Earth Observing Laboratory's calibration lab, thanks to Laura Tudor. These plots are essentially showing the NCAR Cal Lab's references for pressure, temperature, and relative humidity at 3 different temperatures. And then on the y-axis, the WASP temperature, pressure, and relative humidity. And you can see the agreement is very good, and in fact indicated to us that we didn't actually need to calibrate our sensors. The agreement was just this good when we bought the sensors. So that was encouraging. We also did a number of side-by-side comparisons, or a couple, I should say, between WASP and other instruments. So on the left, you can see on the Foothills Laboratory rooftop, we compared WASP canister samples to a 2-liter stainless steel whole air sampling canister. And we also did a comparison, or I guess several comparisons during the summer between the miniaturized anemometer on the WASP instrument to a sonic anemometer at 10 meters. Although the 2-liter canister was analyzed 3 weeks kind of after the comparison, whereas the WASP canisters have to be analyzed really directly thereafter, we found pretty good agreement between VOC, although OVOC agreement, particularly for compounds like acetone, is decidedly less good. The takeaway from our comparison between the sonic anemometer at 10 meters and the Trisonica Mini, which is the anemometer mounted to the WASP boom in flight, is that the comparison is relatively good. This is a polar plot showing essentially wind direction from 0 to 360 degrees, and in distance from the center of the plot is showing wind speed. So you can see paired measurements are on the same color, so those were a comparison between the WASP measurements, which are diamonds, and the circles, which are sonic anemometer measurements there. And the comparison's relatively good, but there are some small differences. To summarize this section, essentially WASP sensors seem to be accurate and precise based on lab calibrations. The WASP measures OVOCs more reliably than it does, VOCs more reliably than it does OVOCs. And we have relatively good comparisons between our side-by-side, between our anemometer on the WASP and the anemometer at 10 meters. So now I'm going to present some results from the Colorado Front Range, most of which were done last winter. So we basically had two sites. We made measurements northwest of the Boulder Reservoir, and at the request of the city of Broomfield, because they were interested in looking at background pollution before doing oil and gas extraction, a site near C470 in Broomfield County. The other site that I've put on this map is a ground-based site, although measurements were made from altitude of about 5 meters, run by the Institute of Arctic and Alpine Research at CU Boulder. And that location was just southeast of the Boulder Reservoir. So they were geographically close, and I will do some comparisons between the two. So we have a number here of vertical profiles of relative humidity and potential temperature. And essentially, there are very small, if any, gradients, vertical gradients in relative humidity or potential temperature from many of our profiles. And in particular, I want to draw your attention to these bottom two cases because I will be showing some VOC measurements from, I believe it's December 2nd and the 29th, a second profile on the 29th of November last year. We also make wind measurements. Those are done during sustained hovers, if I've failed to mention that so far. And so those are basically showing the average and standard deviation of wind speed here along the x-axis with altitude. Wind direction is shown in color here. And essentially, we, as expected, saw that wind speed increases with altitude, and we think we could measure kind of the mean horizontal flow using WASP, the WASP sonic anemometer, and sometimes measure wind shear or changes in wind direction. So the main goal of the instrument that we built, of course, was to sample for VOCs in the atmospheric boundary layer. So these are some of our vertical profiles. This is one example from November 29th. And in particular, I want to draw your attention to a couple things. So first off, this is showing off kind of our range of measurements. We're able to make measurements below 10 parts per trillion and to as high as 25 parts per billion, thanks to the TOGA instrument, largely. I also want to draw your attention to kind of the general vertical structure. So we see that there's potentially some enrichments in various compounds. This is N-pentane, isopentane along the x-axis with altitude, and benzene that I'm highlighting now with altitude. You can see that there's basically enrichment near the surface, potentially related to local sources, maybe C470. And then in some cases, there's also some structure at altitude. And so this is basically from one of those days with a nearly straight potential temperature and RH vertical profile. This was a consistent story for us. We made vertical profiles on several different days, and we often found that there was substantial spatial variability in the vertical direction. We also found that we could basically use these VOC mixing ratios, as many other people have done before us, to look at different sources of pollution. So in this case, I'm showing a plot of isopentane versus N-pentane, and this ratio essentially can denote the influence of oil and natural gas or of urban emissions. And this is relatively consistent with the FRAPPE study. This is a plot from a presentation that Becky Hornbrook did in 2015, showing that kind of at the the Denver suburbs, like Broomfield, are really at the intersection of influences of oil and gas and urban emissions. And that's largely what we're seeing here. I should note that the outliers we have, those green samples, those are our Boulder Reservoir, or some of our Boulder Reservoir samples. And so they're potentially less influenced, it looks like, or less tied to the same influences. We can also look at the ratio of benzene to toluene. And so this is a plot showing toluene on the y-axis, benzene on the x-axis. And again, green samples denote Boulder Reservoir samples, and red samples are from the Broomfield site. My apologies to anybody who's colorblind. I recently found out those are not good colors to put together. They have a relatively strong correlation, and again, their slope, or even the ratio of both of those, is indicative basically of mixed influences of oil and gas and urban emissions. And again, that's relatively consistent. It also looks like we're measuring about the same mixing ratios in terms of benzene as were measured during the FRAPPE campaign. Now that's pretty broad brush because it's hard to see where these locations would be exactly. The last thing in terms of results that I want to present is that we made some measurements at the Boulder Reservoir right to the northwest, and there were INSTAR measurements to the southeast. And so this is a comparison basically showing time on the x-axis and benzene on the y-axis here in this case. And this gray line is the time series of INSTAR measurements at 5 meters. These black dots are the corresponding INSTAR samples to our measurements when we made vertical profiles using the WASPP instrument. And in color here, I've kind of shown the concentrations of benzene at various altitudes that the WASPP instrument sampled. So basically, you can see that there's a relatively good comparison, particularly between our low altitude samples shown in dark blue and these black dots. But there's also a lot of variability in the vertical direction. And you can again see that because the lighter yellow circles often fall quite far off the line. Another way of looking at that is this box plot. And so now I've shown basically our different sampling dates that overlapped with the INSTAR time series. And each box plot shows essentially the variance in our measurements, the WASPP measurements. Each black dot shows the corresponding INSTAR sample at 5 meters. And you can see that the single sample at 5 meters falls within the range of our measurements, but it doesn't capture the spatial variability. And also, because of the spatial variability, it has a very low chance of capturing the mean mixing ratio of VOC in the 100-meter boundary layer. And so, that could be important, I imagine, for various models. And again, we measured several compounds, I guess, that were also measured by the INSTAR program. So that includes N-butane, isopentane, N-pentane, propane, benzene, and toluene. And the story remains essentially the same in all of these cases. We found good correspondence between our low altitude samples, we think, and very much less good correspondence between our high altitude samples and the INSTAR time series. So although there's a ton of information that needs to be captured in terms of a time series, there's a lot of temporal variability. There's also variability in the vertical dimension. So I will now summarize this section too, just in case I forgot to mention anything. Essentially, I hope I showed that we've made vertical measurements of temperature, relative humidity, and pressure that suggest a relatively well-mixed atmospheric boundary layer. These were all daytime measurements. I was restricted to making daytime measurements, and the few times I tried to get up at dawn, it just didn't work out. So this is all I measured. We also made 2D wind velocity measurements, and we think that we're able to capture basically kind of mean horizontal winds and potentially wind shear in these cases. and that these measurements could be useful as well. We haven't really used them in particular yet. We also show that there are strong vertical gradients in VOCs with altitude, even within a well-mixed boundary layer, I think. And that the WASPP instrument can confirm, I guess, really previously identified sources of pollution using VOC ratios. Then the last thing I wanted to mention, which was just basically in the last couple of slides, is that we have good agreement with the INSTAR measurements from the Boulder Reservoir, but also that a single measurement at 5 meters just can't represent spatial variability or potentially the mean mixing ratio of VOCs in the boundary layer. And I think that's an important point. Overall, I think we need more chemical composition measurements to resolve vertical gradients of many chemical species. I hope you think so too. UAS are potentially a really good means of making these measurements based on existing constraints and kind of changes in both fields, in many fields. The WASPP prototype pays special attention really to trying to make ambient measurements and to steering clear of some of the concerns of sampling from a multi-rotor UAV. And we also confirm that there are strong vertical gradients. We're not the first study to show this by any means, but that this can exist in a well-mixed boundary layer, and also that we can really fingerprint sources of pollution even using this new tool. So there are a few potential uses of the WASPP. We really hope it could be useful in the future. Basically, we think that it could provide really helpful information to future ground-based studies by providing more information on spatial variability in the vertical direction and potentially a better estimate of the mean mixing ratios. We also think it could be used for VOC source attribution, like we tried to show here, and that under the right conditions, it might be used for mass balance flux estimates near probably large VOC sources. So using the wind measurements that we have from sustained hovers and the mixing ratio measurements that we make concurrently, that could be useful. Potentially, we would need more samples to be able to do that. And finally, we think that basically these measurements can be used to test assumptions surrounding VOC gradients given the temporal evolution of the atmospheric boundary layer. That's particularly true potentially with higher vertical profiles or the ability to fly in the evening or at dawn more easily. We have a few next steps and goals, one of which I mentioned is to redesign the canister shape to minimize sampling time. So basically, instead of having cylindrical canisters with flat bottoms, we're thinking of trying to round out those edges and hopefully reduce the channeling or inefficient mixing that's occurring in those canisters. We're also really hoping either to use a facility that allows us to make higher vertical profiles or seek out other groups that have certificates of authorization or COAs so that we can kind of resolve vertical gradients in more of the boundary layer. And we like to participate in field campaigns. So if you're interested in collaborating, get in touch with my colleagues at NCAR or myself. We'd be excited. I'd like to give a special thanks to Detlef Helmig's group and the Boulder County Public Health organization for giving me permission to use their measurements in this talk from the Boulder Reservoir. Also to thank Laura Tudor for her help in the NCAR calibration lab, and Rudy Montoya, who painstakingly put together the custom-made electronics boards prior to his retirement. So with that, I'll just say thank you and let me know if you have any questions.
Thanks, Lizzie. Very interesting. I'm sure there are questions.
So when you show these vertical gradients that it is non-uniform, even if you call the mixed layer well mixed, doesn't that also imply that there may be strong horizontal gradients as well? And how would you make that go along with your statement that you hope to do mass flux measurements? Because presumably there you need to measure either over a long time or in a number of different places.
Yes. So as I mentioned, we may need more canisters basically to be able to do that, to be able to do mass flux measurements at all. 8 is probably not sufficient. And essentially, that would also involve kind of very specialized conditions where you had, relatively strong mean flow, horizontal gradients across a large VOC source. So I'd certainly agree with that. Potentially that could be done just by basically loading another canister array on and repeating these measurements. We didn't have the money to facilitate having more canister arrays at this time. And our sampling time limits us to that number. In terms of making measurements over a longer duration, that would be potentially, that could be useful. It might be difficult for us given our flight limitations. So we can stay in flight for about 25 minutes. And so that could, that's the upper limit of a single measurement, basically, in terms of time.
So are you able to get wind measurements both during hovering and during ascents, descents, and horizontal trajectories?
Well, we're currently only making wind measurements during the sustained hovers in the interest of having a wind measurement that was concurrent with our VOC measurements. Now, I think it might be difficult to make wind measurements for us if we were ascending at 5 meters per second. We could potentially try and subtract that out, or look at basically the information within the drone software that lets us know how much it's ballasting against certain wind velocities.
Are there more questions? Steve?
First of all, Lizzie, thank you for your talk today. Appreciate that. And question on your sample cylinders. Instead of redesigning, have you considered taking an approach like putting a dip tube in, or maybe a bent dip tube that would give you a swirling inside the cylinder?
We hadn't considered that, but we will now. That's a great idea.
There are more questions?
Thank you, Lizzie, for the talk. My question is about the second section. There was this plot that every time that you had a hover, there was a negative bias.
Yeah. The second section, so design section, right?
I think so.
Yeah. That one? Or the next one?
Before this.
That one.
It was like, no, even before, like, yeah.
Oh, the profile, this guy.
No, it was like,
That one.
no, not exactly this one. There was this one that you were showing that, yeah, even this one works, yeah.
Okay,
so
sorry.
Every time that you have hover, there is a negative bias, and interestingly, it never gots back. So it's not that the only point of hover. So if you improve your vertical resolution, your negative bias would be even more. And have you considered, like, you know what I mean?
Yeah, I guess, are you looking here at temperature, negative bias and temperature on the descent?
Yes, and also, like, we see, I think, like, in most of them you see, like, whenever there is a hover.
There's a big bias, for sure. So I only use measurements on the ascent for this reason, but go on.
Yeah, so, like, if you plan to increase your hovers, you will have, like, more of these biases. Have you considered, like, somehow just having a correction? Because it seems that I think they are correlated with the time of hover that you have.
No, I think you're right. So I guess I think my presentation was maybe a tiny bit confusing because I'm currently only using basically temperature, pressure, relative humidity measurements from these ascents. And then on the descent, I basically don't use any of that temperature, pressure, or relative humidity data. And part of that is because of these sustained hovers. I mean, another idea that I haven't done because I'd have to basically change the electronic, like the length of electronic cords and stuff, is putting all of these sensors out on the boom. This is something that Becky suggested a while ago. And that might basically decrease this negative bias that I could see during hovers. And at that point, maybe all of the data would be usable. At this point, I've been only using the ascent data, partly based on where I placed the sensor, but also thinking that I didn't necessarily need, or I was more interested in knowing what the vertical profile of temperature, relative humidity, and pressure looked like, but then I didn't necessarily need 1 second data after that on these measurements.
So maybe I missed it, but why are you getting this negative bias?
So I think that might be related to the thermal heating from the instruments, or, well, that wouldn't make sense because that's negative, yeah. But maybe then rotor wash. I don't really have an explanation for exactly what's causing these strong biases.
But the one at 50 meters goes the other way.
Yeah, this one here. That's true. That's extra strange. So that could potentially be rotor wash and how you're mixing up the air. And that's something I've thought about, but I haven't done a good job of discerning.
Do you have a surface measurement, like a 2-meter
Yes.
temperature and humidity?
Yeah.
How does that compare?
Well, typically I start measuring before I take off. And so, you know.
Independent, not from.
Oh, not from WASP. No, although at least the NCAR measurements have a surface measurement at 2 meters, which I could compare. And I've thought about, they also have wind data to compare to.
Yeah, Lizzie, sorry if I missed it, but how do you know these are biases and not just the real atmosphere changing? Do you see this pattern every time you fly, or is it?
I see this pattern every time I fly, but it just seems completely non-physical. I mean, even if there was basically a strong wind and a lot of advection of a different air mass, just sustained negative changes and positive changes during a hover just don't seem real. I don't have a better explanation for it than that.
So I'm not sure if this is, excuse me, I'm not sure if this would be important if there's like light winds, but if there's a pretty strong wind and your boom is facing away from the wind, are you able, first of all, are you able to know that while you're actually making the measurements? And is it possible to have that feedback in to some sort of partial autopilot, or is this something that you have to deal with later when you actually are able to do autopilot?
That would be something I would do later, I guess, when I've basically got more communications between the autopilot and the instrument. Currently, basically, I was planning for that. So I would look at the weather forecast and measure the wind on the ground, basically, and see what the wind direction was supposed to be with altitude. And then I would place my boom in that general direction, at least in 180 degrees kind of leeway. And that seemed to give me, I guess, pretty reasonable measurements, I thought. But certainly I think if the boom was facing directly away from the horizontal wind direction, that would be bad for me, and the measurements would suffer. Currently, that's under like user error, user intelligence.
My feeling was too that this could be real. I mean, there's
That's
no
also
reason
true.
why it shouldn't be real. I don't see why it shouldn't be real. If if after 25 minutes your humidity goes up by 5%, it's totally normal, and that's what it is. So I wouldn't dismiss that.
Okay.
That's question one. Question two, I forgot when you designed this thing. Why not start with the canisters evacuated?
Yeah, so I probably didn't explain that well, but the reason that we pressurized them was largely driven by the fact that I wanted to get duplicate subsamples out of each one, and we already moved up in size from a 50 milliliter size canister to a 100 milliliter size canister, and that was, ever so slightly heavier, bigger, more cumbersome. We couldn't really keep going up in size, and if we evacuated the canisters, then we would end up with potentially, a little less sample than 100 milliliters, and it would make getting duplicate subsamples out of our canisters hard for us, and so.
If
Well-
you evacuate them, the mixing thing goes away.
Yes, the mixing thing does go away, yep.
And the getting them up to ambient should be pretty fast, and then the pump does the rest.
We just would have to have bought another pump and put it, and the one other constraint is just like we were going to use the TOGA analyzer, right? And it needs to sample at ambient pressure, so we would have needed another pump basically to evacuate that canister again from the sample extraction system, which was entirely composed of things we found in the lab.
I still don't see why you can't pressurize them when you start evacuating.
Is there a leak issue, though, if you start with them evacuated?
Well, there's a potential leak issue. Basically, if we pressurize them, any leak is less likely to lead to contamination if there is a leak.
That's a problem that all of our systems undergo.
Yeah.
Well, and this one has particularly, that's why they have to be analyzed within 24 hours instead of 2 days.
Yeah.
There's a greater leak than there is with, say,
Yeah. We did consider that, though, I mean, as an option in terms of evacuating canisters, and that's how most WAS systems work, right? But
Are there more questions?
Sorry, I missed the beginning of the talk. I was wondering, so at CSU, there's a group, they also used drone, they also did computational fluid dynamic simulation. They found some of the places around the drones are certainly very bad places to take samples, while some other places might be better. I was wondering, have you considered that direction at all, like computational fluid dynamic simulations?
there are a lot of studies that have done CFD modeling, basically, for various hectocopters. And so to me, it seems pretty similar. In fact, people have done it for the DJI Matrice 600 Pro. And so they have, various recommendations based on that. And we certainly looked at those. But partly because they've been done so often for so many different types of copters, we wanted to just have one more external check rather than either go off these recommendations or essentially repeat these CFD modeling studies. So.
Are there more questions? I just have one question. So, do you need a special permit to fly this here in Boulder? And is it different here, Boulder, than, let's say, Denver or Broomfield?
So yes and yes. You do need a special permit, which I have to fly. And that just allows you to fly to basically 400 feet to operate as a commercial pilot of a UAS. But then in Boulder, there are a lot of restrictions on where you can fly in terms of property. You can fly, over your private property, but all public property is off limits, except for one aeromodeling kind of park that's near the Boulder Reservoir, which is where we made these measurements. But a lot of county, it varies by county. So I think in Denver, there also might be restrictions. In a lot of big urban areas, there are restrictions because people don't want to be photographed by drones or constantly hear them buzzing around. But in Jefferson County, you can fly them anywhere. You can fly them from the top of Mount Evans, for instance.
So do you have a Part 107 license?
Yeah. I got that when I realized that the instrument was going to work. I was like, okay, now I have to fly it. So.
Okay, there are no more questions. Let's thank again Lizzie.
Thanks, guys.